Hi everyone, thank you for having me here today. My name is Richard Murray and I'm a PhD student in Tyndall National Institute with University College Cork. I know we're all coming from diverse research backgrounds for this session, so you may not be familiar with laser-induced graphene. So I'll outline it briefly first to ensure that we're all on the same page. Laser-induced graphene, or as I may slip into calling it LIG, is a really exciting and promising material for integration with industrial processes at the back end of line. It was first produced by Tor et al. In 2014 by accidentally lasing a piece of Kapton polyamide tape while trying to reduce graphene oxide. The black material produced, to their surprise, was a graphene-like material when examined by RAM spectroscopy, XPS, and transmission electron microscopy imagery. Since then, it has been established that laser-induced graphene can be produced when a viable substrate such as polyamide is treated with an appropriate laser, in our case a 10.6 micron CO2 laser, to rapidly supply the substrate with large amounts of energy. This results in an intense localized heating of the thermally insulating polyamide, the loss of small molecules and groups from the aromatic backbone of the polymer, and its conversion into a graphene-like structure. As can be seen from the SEM micrographs here, the resulting material can range from highly porous all the way up to web-like strands, depending on the formation conditions used. These complex three-dimensional structures are a product of the complex formation process and the presence of Stonewell's defects in the sheetlets allowing for curvature, not normally expected from graphene-like material. Although we focus on the same precursors and substrates that Tor et al. Did in their initial work, it is worth noting that other substrates and laser combinations have been used to successfully produce high-quality graphene-like material, including visible and UV lasers and substrates ranging from quark to Kaizen biopolymers. Like most other groups, we started our research by trialing a few sampling conditions. As we were using a low-cost hobbyist laser setup, we were only able to control the laser power and scan speed for a given raster process. We noted that if we used high laser powers and low scan speeds, we would overablate the substrate, producing no usable material. Similarly, if we used low laser powers and high scan speeds, the material wouldn't convert and instead only partially melt. Within these extremes were a range of values that produced structurally sound material, but also material that presented cracks immediately after its formation. Based off of our initial scoping tests, we established an initial parameter space as shown here. Due to the size of the parameter space, we opted to visually assess and categorize our samples to reduce the scope before conducting more time-consuming measurements. To achieve this, a grid of 60 combinations of laser power and scan speed were produced to determine a viable sampling region. As suggested in our initial parameter space investigation, we see that if laser power is too large, then ablation or cracking occurs, or if laser power is too low or scan speed is too high, then the material is underconverted. What wasn't initially captured was the combination of high laser power and high scan speed producing a brittle fibrous material. We reduced the scope of our investigation to only the green region to ensure fully converted, mechanically robust material in the next step of our analysis. This viable region, marked in green here, was used as the maximum values for a design of experiments response surface. For those unfamiliar, design of experiments is a set of statistical methods that vary multiple experimental factors simultaneously and measure one or a number of response variables. This allows for the reduction of spurious factors to highlight the core and dominant dependencies of a process. But more critically, unlike traditional one factor at a time investigations, design of experiment approaches can capture factor interactions without increasing experimental cost. Iterative application of screening experiments and optimizations can then be used to reduce the number of factors of interest and then determine the interactions between those factors in an economic process, reducing the number of samples required dramatically. The visual inspection on the reduced parameter space graded samples on three features: sample fibrosity, the amount of redeposited residue, and damage to the graphitic material after formation. The most desirable material was selected to be the minimum of each of these features, so the least fibrous, least redeposited residue, and least visible damage. This optimization, which varied both laser power and scan speed simultaneously, suggests that lower laser powers and higher scan speeds would produce more favorable material. However, as can be seen in the desirability heat map, the model suggests that there could be a global minimum beyond what was considered explicitly in this optimization. This highlights one of the main advantages of design of experiments over machine learning methods like random forest or Bayesian optimization. Although they can also investigate complex factor interactions and numerous responses, they also require large numbers of samples to achieve confident results, unlike the linear design of experiments approach, demonstrated here. Further, The iterative use of design of experiment steps can use low experimental cost methods to reduce the parameter space, followed by more rigorous optimizations using more expensive or time-consuming methods. This would ensure that the experimenter's time and resources are focused where they have the greatest impact. Consequently, the parameter space of the next iteration of design of experiment optimization was changed to exclude the higher laser power region and include lower laser power and higher scan speed conditions. This is shown in blue. As we have closed in on more desirable material in this stage, we were comfortable increasing the fidelity of our model by increasing the number of points allowed, but also moving to a more involved assessment criteria, in this case, electrical characterization. Long channel, high aspect ratio, rectangular regions of laser-induced graphene were produced and contacted using a multimeter to estimate the sheet resistance. We did this to reduce our sampling times, as the time taken to land and re-land probes for traditional transmission line measurements would have been burdensome. The use of long channels was to ensure that the contact resistance was only a minor contribution to the estimation of sheet resistance. This approximation of sheet resistance had previously been verified using a test run of laser-induced graphene using current voltage sweeps under traditional transmission line measurement approaches. However, just like with the initial visual design of experiment optimization, this model also predicted the potential for a missed global optimum at lower laser powers and scan speeds than those considered. We redefined our parameter space one last time to include this new region, removing the higher laser power and scan speed regions, which were seen to have higher sheet resistance. This produced our purple region. We found 3 regions of interest, which corresponded to a global minimum of sheet resistance for region 1 and a conditional minimum of sheet resistance for high scan speed in region 2. These formation conditions produced laser-induced graphene with similar sheet resistances, despite one being produced at almost 5 times the rate of the other. This is especially interesting as they are not associated with a constant ratio of power and speed, as marked on the left-hand side of the plot. Instead, this supports the prediction of the model of highly complex interactions between both laser power and scan speed in the formation of laser-induced graphene. SEM micrographs of the regions of interest demonstrate a complex continuum of morphologies that can be achieved using the different formation conditions. These range from highly porous but relatively planar region 1 to the highly three-dimensional region 3 material. However, each of these morphologies would allow for enhanced surface area beyond what would be accessible to a simple planar material. A cross-sectional image of region 1 material also demonstrates the thickness of the reduced laser-induced graphene at about 15 micron, with approximately 20 micron of unconverted polyimide between the laser-induced graphene and the supporting acrylic slip. Note the porosity exists along not just the vertical direction, but also horizontally in the produced material. At the beginning of this presentation, I noted that Tor et al. In their initial work demonstrated that their graphitic material was graphene-like. One of the most convincing arguments that we also demonstrate here is the Raman spectra from our sampled regions of interest. We see the presence of sharp G and 2D peaks characteristic of graphene-like material. As I also noted earlier, the formation process of laser-induced graphene is complicated and involves the loss of smaller molecules and reformation of carbon groups to produce a graphene-like material. However, as marked in the figure on the right by Dong et al., who modelled the process, there remains in the laser-induced graphene an unavoidable amount of unremoved groups, as well as structural defects like Stonewall's defects. The pairs of 2 heptagons and 2 pentagons in the place of 4 hexagons in a graphene sheet. These defects, in addition to the evolved gas molecules, are responsible for the porosity and the curvature we saw in the SEM micrographs. They are also responsible for the presence of sizable defects in the Raman spectrum. We gathered numerous Raman spectra for each of our regions of interest, as demonstrated in our clustering plot. Both regions 1 and 2 behaved similarly, while region 3 deviated, displaying greater variability and less graphene-like behavior. If we analyze our peak ratios as suggested by Ekman et al., we see the ratios of D and D prime peak lie between those expected of vacancy and boundary defects, suggesting that these defects present in the produced material correspond to incomplete reformation of the graphene structure, which may be solvable by a targeted optimization process at a later point. At this point, it's worth noting that more time-consuming experimental methods like SEM imagery and Raman analysis were reserved for the verification points. Consequently, in-depth studies were possible as the experimental resources and time were not expended prematurely. This is one of the key benefits to using an iterative design of experiment approach, ensuring that resources are best used where they would have the greatest impact. Subsequent to the core optimization work, proof of concept humidity sensing devices were produced under the Region 1 and Region 2 conditions. They were then functionalized using polyvinyl alcohol as a hygroscopic dielectric. These devices operated equivalently across a range of relative humidity conditions, produced using saturated salt solutions. This was despite the very different lasering conditions used, with one being produced almost 5 times the rate of the other. It would have been difficult but not impossible to find these parameter sets in a traditional one-factor at a time optimization, and more experimentally expensive than doing it with a multi-factor method like design of experiments. Subsequent to the completion of the core parts of this work, we upgraded to a more complex CO2 laser system, which allowed the control of more than just laser power and scan speed with parameters such as focal height adjustment, image density, so controlling the line-to-line overlap, and pixels per inch horizontal dot density. This system presented a similar but more complicated optimization problem than the initial hobbyist laser system. Despite this, the use of iterative designs of experiment steps has demonstrated that the stock achieved equivalent parameters rapidly. This highlights the ability of multi-factor methods like design of experiments to be integrated in investigative work, rather than just in more traditional home of industrial optimization, as it can be applied to unknown systems to achieve desirable results, but also to replicate an equivalent optimization in a different or even more complex system. To conclude, I would like to highlight the key benefits of structuring investigative work using design of experiment methods, as it allows the informed committal of experimental resources when and where they are needed to produce the best results. Design of experiments can identify multiple reasons of interest, including compromised or constrained optimization approaches for further verification. And finally, I'd like to emphasize that design of experiment is not just for industrial applications. Our work used a cheap hobbyist laser system costing only a couple of €100, and due to its statistical and error handling aspects of design of experiments, was able to facilitate the optimization and tuning of what would otherwise be a challenging system. If anyone has any questions, I'd be more than happy to field them at the questions and answers session or via email at richard.murray@tyndall.ie. And finally, I'd like to take the opportunity to thank my co-authors and supervisors for their advice, insight and support, and to our funding agencies for making this research possible. Thank you.